distribution shift from your training set to your test set. And so the fundamental sort of IID assumption breaks down. And so, what do we do from here? So, one example of this is, distribution shifts, when you don't treat them correctly, can have pretty significant impact. So for instance, here's one thing. So I'm, fairly interested in like things like algorithmic fairness, and this is sort of like a commercial algorithm that was sort of proposed to be deployed to give sort of like risk scores to individuals. And what the model ended up doing is essentially started giving, lower risk scores to Black patients who had the same conditions as white patients. And what happened was, spurious correlation happened. So what the model picked up on was that, you can use previous insurance expenditures as a proxy of like health, and just historical biases about, how insurance companies like to give out money and things like this. It basically figured out that, well, if I use this as a sort of proxy for health, then what I'm going to see is I'm going to think, Black patients are like slightly less sick, even though they might have the same conditions as white patients. And, this breaks when you go from the training distribution, which this spurious correlation exists, to the real world distribution where people are actually sick, and you're not using like previous insurance expenditures to predict how sick they are. So like when you don't handle them well, they can have pretty significant impact. They can, harm subpopulations in this case, or just like catastrophically break more generally.
Wait, so I didn't understand that. So why were Black patients given a lower risk score?
So essentially,
historically, you're saying that, is it because insurance companies were paying less money to Black patients, and so they thought they were healthier because fewer things were happening?
Yeah,
I see.
Yeah. So the idea is just like if you've been using, there's just some spurious correlation between like insurance expenditure and health that ended up being biased based on how insurance companies historically have chosen to give out money. So our task will essentially be, we have a set of potential distributions. So you can maybe think of this geography, think of this as, distributions of demographics, time, whatever you like. I'm going to stick with the example of, geography here. And the idea is like, for instance, I get to see some distributions I get to train on, right? So this might be 3 different hospitals. And so then I get to, learn some model. We'll assume we just want to do this, think of it, machine learning is all just conditional expectation, will be sort of like my reduction for this talk. And we sort of learn some model to do this prediction. And the goal is when we get to the real world and we get a real deployment, in our real deployment setting, the model we've learned from our training set, works well. So again, I learned from, 3 different hospitals from different continents, and I'm generalizing it's like maybe a new continent. It's sort of like the conceptualization to think of here. And so, you might think like maybe your training set is just one distribution, maybe it's like E distributions. So if we're going to think about each of these settings. And so this talk is going to focus on 2 things, basically to help us navigate distribution shift like a pro. We're going to think about like model development. How do you actually do what algorithms can you use for various settings of distribution shifts? And then model evaluation, which is like what I've been thinking about most recently, is sort of like how distribution shifts sort of like interact with evaluation and how this might inform AI policy. So expected takeaway is my plan is not to go in depth into any method, mostly to paint the picture of the spectrum of types of problems you might see, and sort of like give you an idea of the solutions. And with lots of citation of my work and other people's work, of methods that you might apply, such that when you're faced with this problem, you can sort of like map back to, okay, this was the setting I remember. Maybe go back to these slides and find the relevant papers and methods. So some preliminaries is so I tend to think of most of these problems with the language of causality, and I do this because I think causality gives us sort of a specific and succinct language to describe what's changing, what's not changing, beyond just P of XY doesn't equal to Q of XY. We can be a bit more specific about what part of the joint is changing and what kind of the joint distribution is like sort of like staying the same. And so why is this the case? So a brief primer of why we might use causality. So we can go back to early 1956 and think of Reichenbach's common cause principle, which says if you give me 2 random variables and they're correlated, they either correlate because one caused the other, or there's a third so-called Reichenbach variable that sort of causes this correlation. And I'm going to leverage causality quite a lot in this talk. So I think it's important to get some basics down. So first, you can think of X, a causal relationship, right? So in the first case, X and Y are correlated because X causes Y and Y causes X. So in this case, it rains outside, causes you to grab an umbrella. pretty straightforward. The other is sort of like you might have it because it's a mediator. So for instance, you might say, okay, there's a correlation between the time of the month and how many umbrellas I see. But that's only because it's mediated by sort of rain, right? So you get different distribution of rain based on the month, right? So if I got rid of rain, this correlation, for instance, wouldn't be there. The third is that you have maybe a confounder, so a common cause. Well, you can't really see that on the screen. Okay, but the light is just a third variable z. And so maybe, it's you see a correlation between the number of umbrellas outside and how wet it is outside, but that's not a causal relationship. That's sort of just confounded. When it rains, both it gets wet outside and more people have umbrellas, right? So again, these are all correlations. If you built a machine learning model based on sort of like any one of these things, you would probably get a pretty good predictor. Here's why causality is important for distribution shift, right? So like if I intervene, which means I just have a magic wand that can change the distribution of a variable, right? If I just like intervene and now, I passed a law, everyone has to carry an umbrella around this many times a week, right? Independent of whether or not it's raining, right? With this distribution shift, now my machine learning model is broken, right? So like whatever predictor I had for predicting how wet it is outside from umbrella now breaks because of this distribution shift, right? Similarly, if I would just say I had a magic wand, I could just make it rain outside arbitrarily and change that distribution. Now, whatever correlation I've made between the time of the month and the number of umbrellas that are outside is also broken. Now my machine learning model is no longer accurate, right? So you can think of this magic wand as like, I made COVID happen, right? So anything COVID broke, for instance, anything that wasn't quite causal, all those spurious correlations get immediately, got rid of, right? And this is why I think about causality or whatever else you want to call it. If you don't like the word causality, is important. What you see here is, so, if I have a causal relationship, it doesn't matter how I make it rain, you're going to grab an umbrella, whether or not I have a magic wand, whether or not it's just, climate, whatever, right? And this is sort of like the robustness of causal relationships, right? It's sort of like we have this invariance to intervention. So this do operator just says, for all causal pairs of y, it doesn't matter how I set it, my conditional expectation, my outcome will always be the same, right? And so you can already see where I'm going with this, right? For instance, right? If you can identify this causal relationship, you get lots of nice properties, mostly about robustness of distribution shifts. And so we're gonna like leverage this quite a bit in this talk. So the main thing I'm gonna think about is sort of like what I'm gonna call like latent shifts. So you have some unobserved thing that's driving sort of your distribution shift, right? So like for instance, in the healthcare case, you have like social determinants of health, which might be unobserved, and you have like, X, maybe some measurements of your health or whatever, and your outcome is like some diagnosis or whatever. So what you know here is because U touches everything, this like sort of like latent thing that I don't see that sort of affects everything, because it affects all my observables. What I'm gonna see is just like, P of X doesn't equals Q of X potentially, P of Y doesn't equals Q of Y potentially, like both conditional expectations both ways may not be equal, right? But obviously, U is just an unobserved confounder. If I somehow did observe it and I just condition on it, I would sort of like get equality, right? So I'll be able to sort of like learn a predictor that has both U and X. Again, I don't see U. I learn a predictor that has both U and X and get a good prediction for Y. But that's not the case. So then the question is, in this setting, which is like fairly general, I'll show, how do we learn a model from a distribution P that we get to see, that generalized distribution Q that we may see some parts of it, which would be sort of like the what this talk goes over. And so again, no free lunch. We have to make some assumptions about what Q is and what type of information about Q that we have access to. And so I'm going to go over some levels, what I'm calling levels of insight about Q, right? So best case, you get to see labeled examples, right? In some sense, maybe if you have small sample sizes, problem is interesting, but if you have a lot of samples, this problem isn't that interesting. What about when you have unlabeled samples, particularly when you have unlabeled samples with side information? So side information I'll get to in a few slides. What can you do in this case, right? So you don't have labeled samples, but you get to see X. Like what hospital you want to generalize to, and you have some information about that hospital. And then the others where you have no samples, but you have some idea about like relationships that you think might stay the same. And the way you might specify this is with a causal graph, for instance, to sort of specify what changes and what doesn't changes. And what if you have nothing? Are you completely screwed? Not quite. And I'll talk about this briefly as well. And so just to, again, hone in on the high level thing. And so like when we have labeled samples, I'm just going to give you the answer before I get into it. We're just going to like fine tune or do transfer learning, easy. When we have unlabeled samples and we have side information, which I'm going to call this proxy causal graph, we can do domain adaptation with proxies, which again is very general. You can recover like base optimal models in your target distribution without any labels, right? When you see unlabeled samples, you can do it under like covariate shift and label shift, which I'll talk about briefly, right? And so if you only have unlabeled samples, if you have like covariate shift and label shift assumptions hold, you can still recover everything that's fine. Then what I spent most of my PhD thinking about is sort of like when you don't have any samples and you're just trying to do domain generalization, right? And you're just sort of like, I don't know what hospital I'm going to generalize to, but I know I'm going to have to generalize to some hospital. And I get to see some set of hospitals during training. What can I do to sort of like handle that task? And then when you're completely clueless, you should still do domain generalization. It's going to be my claim. And this also gives you some robust properties. And I'm already going slower than I anticipated, which I should have known. But I think the more important thing is sort of like AI policy and evaluation and how this interacts with the effective distribution shifts, right? When we have to like train some ChatGPT that's trained on the internet, and you might think the internet is IID with the world, I'd argue otherwise. Then, what can we say about, our ability to evaluate and expect similar performance in the real world? And so hopefully we get to that. So the first thing is fine tuning, right? So like you have Q of X, Y, you have lots of samples or maybe small samples. You can recover, the best predictor for Q, which I'll just call the conditional expectation here. You can still recover this if you have unlabeled samples. This should be obvious, right? You have large sample size, you can just ignore.
Why do you need to use P at all?
Exactly. So this is the first thing. You just like start with random initialization, just train on Q of X, Y.
Yeah.
So you don't need P of P at all. So that's the first thing you might do, right? You might choose to fine tune, right? Maybe you think like somehow you have more samples effectively. Why not use it if you have it, right? And so if you have large sample size, you can just use P at all. You can just not use P at all, or you can fine tune. If you have small sample size, then again, this is the setting where you might want to fine tune, or more importantly, you might want to do transfer learning. And so what transfer learning, what I mean here is, when you train from scratch, you want to predict car, truck, whatever. You start from some random initialization, you train for this predictor. Transfer learning, what you do is suppose you still want to predict car and truck, but you have some model that's already trained predicting cats and dogs, right? Presumably, maybe like, your images are images, the high level semantic features, this model has already learned. So you might choose to freeze, for instance, the featurizer and only retrain the last layer, right? So if you have like not that many samples, this can be very helpful. I mean, this is used a lot in like maybe healthcare where you often don't have a lot of samples. So maybe you take a model that was like trained on ImageNet, for instance, and you just do transfer learning where you retrain just the last layer with the idea that sort of like your features are sort of like well-defined. And so we have some evidence for this, right? So like, this work at Pradeep Kumar's group who was here at some point shows that, ERM learns pretty general features, right? So like the featurizer, if you just do ERM, pretend nothing is wrong on some large diverse data set, learns pretty general features, which means you can just like retrain on top of that, and you still get sort of like really nice guarantees for specifically out of distribution generalization. And this has been shown to work, right? So work out of Steinberg et al. And Nigam Shah's group at Stanford, they show that, large language models are effective representation of like EHR data. So like they learn pretty robust semantic features that you can now use to do, whatever downstream task you might be interested in. So this is like the easiest setting, right? You have labeled data limitation. Labeled data is expensive. In fact, if you want to help effectively create label data, I don't know what this is because I don't want to advertise things I don't know, but people will pay you to sort of like help effectively have labels for RLHF, for LLMs right now, but you have to get paid for it, right? And label data might be impossible. Like, how do I get label data for COVID, for instance, right? So like, so that's the main limitation. If you could, you would, but you can't. Can I still get like, a great model for Q without labels? Yes, but we need proxies, right? And so this is the work that we've been working on over the last few years with a lot of like really, really great people. This method we're calling like proxy methods for domain generalization, which is using a lot of ideas from causal inference, specifically like semi-parametric causal inference. And so the idea here is that sort of you still have this latent shift, you have some unobserved thing that changes everything. Say it's like COVID, for instance, changes all your X's, changes all your Y's. And so you have, if P of U and Q of U aren't the same, then, predicting X from Y, the relationship might change. But again, like I said before, if you condition on U, everything is fine. And so an example of this is sort of like, I might have social determinants of health. So one of these might be like, economic status or education. And this, it doesn't feel natural, but it's been shown that this affects, health outcomes, right? If you want to predict from, say, a chest X-ray and predict like pneumothorax, which is just like whether your lung is collapsed or not, if you go from, say, a wealthy neighborhood to a not so wealthy neighborhood, the two predictors there might differ because of spurious correlations with various things. And so now if I want to like only learn, say, from wealthy neighborhoods and I want to generalize to less wealthy neighborhoods, but I don't have labels, what might I do? And so what I might do is to sort of observe some proxies. So they're not labels, but proxies are essentially sort of things that are similar, that are proxies of the unobserved compound. So here, for the sake of social determinants of health, you might say, okay, well, I don't have labels, but I do get to see like patient information. So like when I come in after fill out a form, I see how old I am, I see what neighborhood I live in. If I just look at your zip code, I have some idea of like your wealth, there's some variance, but like it is a proxy of these various determinants of health. And I have proxies. So proxies are mediators between my features and my outcome. So here, I see an X-ray example we like to use is like, oftentimes doctors write notes. It's like a doctor's notes can be a mediator to the actual predicted diagnosis of whether you have pneumothorax or not, right? And so turns out that if you have these two types of information, these proxies and this mediator, you can recover EQ y given X in your target domain, which I'll just call target domain your Q, source domain your P, where you get to train on as your source. And so, yeah. And so what are some examples of proxies, right? So if I'm in healthcare and I want to maybe what's your base healthcare access, right? I can't really ask you that sort of weird thing, but it's a proxy for like healthcare access, might be zip code or like whether or not you have health insurance or how good your health insurance is. So like we do have proxies all over the place oftentimes, right? Maybe you're in finance, right? You want to sort of figure out risk taking, right? It's like some latent thing that you think affects your observables, but you can't necessarily have a measure of that. You might look at, well, how many credit card applications have you made in the last like 2 years or so? Or like I can look at, what your distribution of like purchases look like. Might be a proxy for risk taking. If I want to look at like marketing, I'm an Instagram influencer for whatever reason, and I want to look at brand loyalty, I can like maybe give you a survey, or I can maybe look at how frequently you're sharing referral codes, things like this. So we just have like proxies everywhere that are sort of like noisy views of like the things we think is causing change and it's breaking our classifier. And the idea is that we can leverage this proxy to do it. And I won't get too much detail, but the trick here is sort of like using bridge functions from semi-parametric causal inference. So bridge functions is essentially a way, they're more like a link function between observable proxies to the unobserved confound. It's sort of like the idea there. And the idea is that if you, with some assumptions, right? So if I assume the proxy graph I just described earlier, where you have like noisy views of your latent confounds, I assume positivity. So, like things that exist in my source at the latent level also exist in my target, or vice versa. I guess things that exist in my target also exist in my source. And then you have like, positivity, which is all that means. Then what ends up happening is that if I want to estimate EQ y given X, right, there exists this bridge function, which I can learn from my source domain. I need label data to like estimate this bridge function, but this bridge function is shared between my source and my target domain. So H of P, I can replace it with H of Q. They're exactly the same, right? But I need labels to learn it, but I have labels in my training data set. So I can learn this bridge function, and then all I need is to have Q of WC given X, which I assume I get to see in my target domain. So I don't see labels, I just get to see these proxies, right? And because I can sort of like estimate this bridge function in my source domain, I can recover basically the beta optimal model for Q without labels. So again, I don't even need labels, right? And so this is that. This line of work I really like because it's sort of like it lets us leverage information that we think is probably everywhere and we can sort of like get access to the settings. Maybe there's not everywhere, but at least like, in things like hospitals and things like that, we have information about like where people live, what kind of jobs they have, maybe, how old they are, and these things that we can leverage, that we shouldn't use as features directly, because that also introduces bias, but can help us adjust our predictions. And so, so this is estimable from our observed distribution from P, and then the latter is estimatable from our distribution over our target domain. And so actually this is the most general result, right? So this is if everything is continuous and like arbitrarily large dimensional, we can recover this, right? But like this isn't always the case. There are simpler tasks. So for instance, if everything is categorical, you don't even need proxies in your target. You only need proxies in your source domain. And this is like a very, very clever proof from Kuroki and Pearl, where they basically show that if you have like a bunch of categorical variables, and this is a trick I like actually that I'm going to try to use, is that if you write everything out as like just a matrix of probabilities and you just rearrange things, then things just become observed, like identifiable up to like rotations with SVD. So like actually what ends up happening is if everything is categorical and you write, what is P of Y given X, and you do the factorization and you write everything as matrix form and you try to solve for Q of U up to rotations, it's just SVD. And you get like the orthogonality is just the probabilities of U, which you're summing over anyway. So like the order doesn't matter. And so you only just need Q of X. Sorry, I didn't mean to say that, but I just like that trick that they did. The other one is if only use categorical, but everything else is continuous. You can use a similar idea, but you need to use like WAE or VAE type methods. And you can sort of do a similar thing where you can recover U up to like rotations, and then condition on U to get your outcome. And if everything is continuous, then you do indeed need these proxies in order to sort of like adjust with bridge functions that let you get the best version of U. So like, I'm not going to go into detail because I'll just spend the whole talk here. But like, please feel free to look at the paper. I think these are some interesting and useful results. And so, for instance, here's an example where we sort of are looking at the hospital case and we're predicting like, whether or not somebody has a condition or they don't have a condition, right? And so we have a shift that just like induces the prevalence of whether people have condition based on their sex. So, when you're female, we vary how often you have a condition. So this is like, a label shift. It's also a covariate shift, but you're also changing sort of like the distribution of like conditions and say your chest X-ray, which is our X here. And so we just like make the shift bigger and bigger. So in our training domain, we get to see, prevalence is 0.1, and we just make the y-axis bigger. So we're inducing a bigger and bigger shift. And what we'll see is that, like when we look at ERN, right, the empirical risk minimizer just gets worse and worse and worse, right, as we increase the shifts. And our proposed method here, is very close to the oracle, right? So it's just sort of like staying fine the whole time, right? It's maintaining performance the whole time. And again, this is the idea that, when we have some idea of what the shifts are, we can often, or the source of the shifts, we can often find proxies, and using this bridge function method, we can sort of figure out how to adapt as we have a distribution shift. And what if we have no concepts? I'm not going to spend much time talking about this either, but it's still fine. Concepts might be the trickier thing to get, things that mediate X to Y. But in that case, we just need many domains. We need many distributions. So if I don't have like doctor's notes, but I only have like the survey from patients, I just need like a bunch of hospitals, and that's sufficient, right? If I have concept, I just need one hospital to train on. If I don't have concepts, then I need multiple hospitals, which again isn't the most craziest thing like to ask, I think, in practice, at least for like the healthcare domain, which I often think about. And we can still recover this predictor for our target domain. So limitation here is that concepts may not be readily available. And so when they're not readily available, then we need multiple domains. And this still doesn't solve all our problems. We still need that, P of U given X is sort of like in the convex hull of our training domain. So I still need like diverse domain, right? If I just need like if I have some limited set of hospitals, it still doesn't tell me enough to generalize to new hospitals. But if I have a sufficiently large set of hospitals, the diversity sort of like lets me generalize and adapt to anything inside the convex hull. So it's still, limited. You need multiple hospitals. You still need proxies. So what if you don't have this? Then what can you do next? And so like I don't have proxies. I don't have multiple domains. I just have a hospital. I just have a bunch of XYs, and I have X's in my target domain. Can I still get E of Q of X? Yes, still, but in less general settings, right? And so this would be work that there's a ton of work on, just Google covariate shift, label shift. But the idea is just like, okay, if I assume that U only affects X, but it doesn't change Y, then I have that E of Y given X. Let's see. I still have that E of Y given X isn't quite equal, but I know that P of Y given X is equal. Okay. And if I have that U affects Y only, so it doesn't affect X, right? I know that like my predictor might still break because my distribution of Y is not being changed, right? But I know that this conditional, right? Again, because of causality, causal parent, the P of X given Y is invariant. And so what does that let me do? So like I can do covariate shift solution, right? So if I just, what I want to do is when I have covariate shift where my, latent confounder changes the distribution of my X, my covariates, at a high level, I just want to transform my X so that it looks like my P, right? And this should be obvious, right? If I transform my X so that it looks like my P, and I think that my, my mapping stays the same, P of Y given X stays the same, then I just need to reweight, right? So if I reweight with Q of X over P of X, so maybe I learn a classifier to predict the two, and I just use the probabilities to do the mapping, and I can recover E of Q of sort of like any quantity, which could be, what my loss function is if I'm optimizing, or it could be my prediction. And so another approach I can do is I can do domain adversarial training, right? So I can say, okay, I have labeled data in my training. I only have unlabeled data in my test. So what I can do is I can like sort of have a loss function based on a featurizer. So not the predictor yet, just the feature mapping. And what I can do is I can regularize this representation such that a classifier can't tell the difference. So I like GAN style, like adversarial training style. I sort of like try to learn a feature map such that a classifier can't distinguish between my P of X and my Q of X. And again, this has an effectively the same method where now if I think the mapping stays the same by assumption, I can sort of like generalize now because my P of X and Q of X looks the same. And so then I can just predict based on that, and presumably that prediction is just learning the map that's invariant for both of my domain. And then label shift has a similar solution. I'm not going to go into it, but there's a very nice paper reference here out of Zach Lipton's group at CMU that sort of does a reweighting type thing based on what's the word for the matrix you get, error matrix. Sorry, confusion matrix. Thank you, whoever said that. Yeah. So yeah, from your confusion matrix, you can do a similar type of reweighting to adjust for label shift as well.
But don't these necessarily assume some kind of reasonably nice relationship between P and Q?
So you need overlap is the main thing. So you need that like so basically you need positivity. So every like measurable sort of the measurable set in your target has to also be measurable in your source.
Right, like P of X can be 0.
Yeah, exactly. Yeah, so that's the main thing. So
and also, I mean, but that weight function can't blow up.
Yeah, that's one of the things. Yeah, if that's 0, it blows up. And so you need sufficient mass over your Q of X in your P of X.
So
right?
Aren't there cases where like P of X you're training on some part of the support that you just don't see in some subpopulation?
Yeah.
Shift.
Yeah.
What happens there?
Nothing works. Is what I can say. Yeah. I think in that setting, like using something like the reweighting breaks for obvious reasons. Like you said, everything blows up. If you do something like adversarial training, like your method won't break. Like you still don't have as much of a robustness on that on the place where you don't have any support. In the domain of X where you have no support, but the method at least won't break, and the things that you do have coverage over, you'll do well on. But if you don't have positivity, that's like a first assumption, right? You still need that. You still need that your target domain is a subset of your source domain. Otherwise,
can you test positivity given samples from P and Q?
Yeah. So like it's a simple thing to do is you just like train a classifier to predict whether or not like a sample is coming from P or Q, and anything that has too high of a or too low of a probability.
Okay. So it's a heuristic.
Yeah. Sorry?
It's a heuristic.
Yeah, it's a heuristic. Yeah. I mean, but like, train a classifier, it are like upper bounds on like, say like, or like low bounds on total variation, like upper bounds on H divergence. So it is like it's a heuristic, but it is like, like with large enough samples, it does recover some
Large enough
averages.
samples, yeah.
Yeah. So like, since, everyone is interested in LLMs, these days, actually, this idea of in-context learning is related to this idea. So like recent work have thought about sort of like COVID, like, part of the reason things seem to do well out of distribution is because you're actually sort of doing this covariate shift assumption from prompts. So prompts are in some sense like some conditioning that aligns the distribution of what the LLM has seen with what you want it to see. So an example of this is, if you ask two questions, right? You're talking to a teenager, write a poem about gravitational fields, versus you're talking to a physics graduate, write a poem about gravitational fields, right? Those are two very, very different things, right? Usually we would just like say, write a poem about gravitational fields, which means we would sort of like marginalize over like all the different contexts, all the different like maybe sub distributions that we might care about. But what happens when we prompt is that we actually zoom in on a very specific. So we solve the covariate shift problem by zooming in, right? So again, right, our Q of X is some subset of our P of X, right? But we don't know what that is. If we don't know anything about Q of X, we essentially we just sort of like guess we just marginalize over all of P, so we get like, potentially very terrible performance. But if we prompt, right, and what the prompting presumably is actually doing is sort of like contextualizing what Q of X is and sort of doing the covariate shift alignment in the background for us. And this is sort of why if we look at a lot of sort of out of distribution generalization benchmarks, like LLMs just seem to do very well. But like if you take out the prompting, this isn't quite as true. Right, and so like so it's sort of a more general notion of what we used to call marginal transfer learning, where we sort of like learn an embedding of our representation. Maybe it's like MMD or something. Like we embedded some Hilbert space and we sort of like try to figure out distances, and we use that to sort of like adjust our classifier. Now we can just like immediately sort of like just tell you what the prompt is, and that allows you to do some covariate shift adjustment. So like, this idea of sort of like, covariate shift, label shift, proxy shift is still relevant. We just may not be doing it explicitly in sort of like modern day models. And so, but what's the limitation of this? Is that, covariate shift and label shift are very, very strong assumptions, right? The idea that like only the marginal, only P of X changes or only P of Y changes, nothing else changes, is quite difficult, which is why we needed like proxies to do something a bit better. And so like, it's a very, very strong assumption, and like lots of papers like this one I like have shown that, like they actually don't hold in many settings that people think they do, which is why some of the solutions don't work as well as we do. So now we're at the limit of sort of like where we can, like, this is like sort of like the least amount of information I can have, right? I want to generalize to Q, right? And I have only Q of X, that's all I have. If I don't have that, then I have nothing, right? And so, so far I've sort of like hopefully painted a picture of like with various types of information, what kind of method might you use? But the next step is sort of like, what if I know nothing about Q, right? So I don't get to see Q at all, right? I just think, if I think Q has nothing to do with P, then it's my fault for trying to generalize, right? That's just a dumb decision. But if I do think like P is related to Q and Q is related to P in some way, how might I sort of like do this if I don't actually see any information about Q? So getting like, E of Q of X is probably not going to happen, right? But we're not completely hopeless. There's still stuff we can do. And so this is going to be work on domain generalization. So the idea here is just like, I'm going to assume now that I have multiple P's. So I get to see multiple, say, hospitals from the world, right? And so this is sort of going to be my replacement for like not seeing anything from Q. And what I'm going to assume is that I want to learn some phi of X where like EQ y of phi of X is the same as EQ y, EP y of phi of X, right? So the idea is just like, there's some latent space where maybe I have to throw away some information because they don't generalize. But like, if I'm in physics, there's some law of physics that I can like hone in on that gives me not as good of a predictor, but still a stable, good predictor that I might use. And so this is sort of like what domain generalization is trying to do. And so the assumption here is we're going to think that, we have some X, our feature space, it's partitioned into two types of features. There's some stable features, there's some unstable features. What do stable features mean? It means that, this thing that I wanted holds, right? So my predictor based on this stable features is the same from my source to my target domain. My unstable features, what I'm going to call spurious features, this is not true, right? If I condition on my spurious features, I can do some changes that can be, potentially catastrophically bad when generalizing. And so our goal here is going to be, can we isolate ZC here? And so an example of this is for people who are really, really interested in sort of like trying to predict pneumothorax from X-ray images. So like, did your lung collapse? This feels like it should be a very easy task, right? You just look, is your lung intact? Yes, then you don't have it. Is it not? No, then you don't have it. So like machine learning models should be able to help us with this. So what ended up happening is that they collected a bunch of data of no pneumothorax, some with pneumothorax. And then, what happened was actually, if you notice, there's a chest drain here, right? And this is the solution. This is the medical fix for pneumothorax, is that they insert sort of a chest drain into your chest. So what happened was that a bunch of the samples that they collected were people who were already treated. And so they still had pneumothorax, but they had already the solution there. And so guess what happens? You can predict is that you would get somebody who had pneumothorax in the real world but hadn't been treated yet. And it would be like, whoa, they have no pneumothorax. And you would say, why? Well, it's obvious why. It's because the model just ignored the chest totally. I was like, okay, do you have a chest? Do you have a chest drain in your chest? Yes, you have pneumothorax. No, you don't have pneumothorax, right? And so this is an example of a distribution shift where like the distribution shift is, P where you had already intervened and Q where you haven't intervened, right? And this is also an example of where you have two sets of features, right? You have the chest X-ray part, right? That's ZC here, which we think is stable. Really doesn't matter. Your chest is either collapsed or not. Your lung is either collapsed or not. And there's the spurious feature that's also a good predictor. That's the chest X-ray. So this might be our example of what ZC and Z spurious might be here. And so if we go back to the beginning of our Reichenbach common cause principle, we have three variables here that are related. Specifically, we care about ZC and Z spurious and Y. Why might they be correlated? Well, the few reasons they might be correlated is that we might have causal, right? So then we have that, this is the example of the pneumothorax. My context is E, right? So this is like my hospitals, for instance, right? My hospital sort of like generates my distribution of features, my distribution of X. I think my ZC and my Z spurious are mapped to my observed feature space by some invertible function. And I think my ZC is causal to Y, but Z spurious is not causal to Y, right? Again, causal relationships are preserved, right? And non-causal relationships may or may not be preserved, just depends on the context, right? And so from this, we have two properties. We have domain invariance, which just says that, my ZC is sort of, my Y is independent of my context or my hospital or my distribution. If I condition on ZC, that's one conditional dependence that this graph sort of like implies. And the second is that Y, ZC, and Z spurious are conditionally independent of each other if I condition on Y and E, right? So we're gonna use these two solutions to sort of like help us try to identify ZC, because if we learn a predictor from ZC, then we have sort of like we expect stability or like a robust predictor to distribution shift. We have an anti-causal setting, which I'm going to skip, but it has the same sort of properties, conditional dependence properties as my first one. And then we have this third property, which we call the fully informative causal feature setting, where actually ZC is a confound for Y. So it's a cause of Y. So that relationship is sort of preserved, but it's also a cause of Z spurious. So an example of this is, you want to predict hospital readmissions, right? And ZC is sort of like the severity of the condition, and like your spurious features like the length of stay, right? Obviously, if you have like a very, very severe condition, it's going to cause you to be readmitted, but also it's going to cause you to stay in the hospital longer, right? So it's a common cause. So I would get a really good predictor of what your, severity of your disease just by length of stay. But like if I just made you stay in the hospital for like 20 years instead of like a week, right? That wouldn't change presumably your outcome. And so for a long time, people, because of sort of like, oh, look, domain invariance is here for everything, people just wanted to use domain invariance, right? But what turns out is just like actually domain invariance, this third domain is very easy, right? And it's very easy because Z is a common cause. Remember earlier I said if you condition on U, everything stays the same where U is a common cause. Well, here ZC is just a U, which I see, right? So if I condition on ZC, then everything is invariant and everything is fine. So I can just totally ignore this case. And now I can consider the second condition, right? And so this first condition, there's been a lot of work on it. It's very, very difficult to get to actually work for reasons I'll show in the next few slides. But the second condition is a bit more reasonable. And now, by observing this, we can now say, okay, actually, this gives us very good results in general settings, and it's not limited. And so what is domain invariance? So the main thing we want to do for domain invariance is to say that we want to learn a phi that maps to some x or some latent space, such that the optimal predictor for every p, every domain I see, is the same, right? So this is like sort of like the main invariant risk minimization, the paper some of you might be familiar with, was the main thing. So the idea is just like, suppose I have a digit and a color, right? And like, I think my color is spuriously correlated with the digit. The idea is just I want to learn a representation of my image, my digit, such that the optimal predictor on top of this representation is exactly the same, right? So what this means, conceptually what this means is just like, if I have this is true, then like the things that change, my featurizer is ignored, right? So in principle, if I'm using color and color has a different relationship in each distribution, then the best predictor will be different because it will depend on color. But if I get a representation where the best predictor for each domain is exactly the same, then the idea is just like, okay, well, I've learned to ignore color, which is the spurious feature, and I've sort of learned the invariant thing, which is just a digit. Turns out that for this to actually work, you need sort of like the rank of your spurious features to the number of domains you see to be on the rank of your spurious features. So like if you think that your spurious features is like background in an image, well, count how many pixels you have. And that's how many, in principle, worst case at least, that's how many domains you need. So like, it's actually fairly tricky to get this to work because of the large number of domains you need in like high dimensional settings. And so we propose this other setting, which is sort of like, what you want to do is you want to leverage this second condition dependence property. And what you want to do is you want to learn two feature representations, right? So you have your phi c and your phi spurious. By their name, it should be obvious what they're trying to do. So the main thing is you want your phi spurious and your phi c to be conditionally independent of each other, given y for every domain you see. So for every hospital you see. The second is that you want your phi c and its predictor, which is shared across domains, to be optimal on average across domain. And what you want is you want the concatenation of your phi c and your phi spurious to be optimal per domain. And optimal per domain means like each domain gets its own predictor, right? Use phi c of this right here, you sort of like isolate the invariant thing, right? But you need all the information to stay put, right? Because like, for instance, I can just make phi c independent of noise, right? So I can have phi c it still needs to be constrained, otherwise they're trivial solutions. And so the way we get around it is we say, okay, well, I want to recover all the information. So I'm going to have a second featurizer that's allowed to use whatever information it wants, so long as it's conditionally independent of my invariant thing that I want to use, right? So I'm only going to use this for prediction. This is just here strictly to constrain the model during training. And the thing is that to allow this spurious to use whatever information it wants, it gets us a unique predictor for each domain, which means that each domain can leverage all the spuriousness it wants to get good accuracy. But we're never going to use this for prediction, actually. It's just there to maintain our first sort of like condition independence property. And so I'm going to skip this for the sake of time. And just so that, when we implement this across like our causal graph and our graph C, which again, we assume doesn't actually need anything, it still does comparable. Well, it blows out ERN, which we think should break. It also beats all the rest of the models. And in the case where we're in graph C, where we don't actually think we need to do anything special, right? It doesn't break anything. And the other methods that are meant for domain generalization do break things because the assumptions just don't hold, right? And so this method seems to work very well. The issue though is the limitations is it's noisy, right? Like it's concerned about the worst case shifts, right? So like in the first one, the domain invariance, right? This is sort of like the good and the bad, it's a double-edged sword. In domain invariance, if something was spurious, but it wasn't spurious for your set of training domains, you kept it, right? Which is good because you get whatever accuracy boost it provides, but it's bad because if you see a new domain where it no longer works, you break catastrophically. Our method doesn't care whether or not you give good performance or preserve within your training domain. It just cares whether you satisfy the condition that the causal graph has specified, which means that if there's information that's useful, but it's spurious, but it's used for your training domain, it's going to throw it away, right? So then, but it gives you the best robustness of worst case shifts, right? Which is sort of probably what, it depends on what you want, right? If there's something you care about, then you want to use our method. If it's not, then I'm not sure why you were doing this in the first place, right? You should maybe just do ERM and hope things work out well. Yeah. And so this is sort of and I was going to talk about the Clueless. So when you don't know anything. Oh, okay. Okay, great. I'm just gonna skip here so I can get to the evaluation part. Turns out that, you know, we have for the generality of domain generalization. So like, how can you say, oh, I don't actually know whether or not my graph is right or not? Well, it turns out we've shown that our method works well for these three graphs. Turns out that these three graphs actually specify, if you think that you have some subset of features that's stable and some subset that aren't stable, and they're correlated, they can only be correlated for those three sort of Reichenbach reason, right? Either causal, anti-causal, or you have like a common cause, right? And our method works for all three of them. So like, unless you can define a new way, which actually would be just combinations of them, if you have like combination of all three, we're not sure what you would do there. But if you just have like one of these settings, then our method should do well. And you don't really even need to know which one it is, because our method does well across all of them. So when you're clueless and you're just like, okay, well, I don't know whether my graph holds, if this sort of like, you think there's some spurious feature that you want to ignore and some non-spurious feature that you want to keep, then this method should satisfy sort of like what you need under distribution shift. Again, under the condition that you're sacrificing probably average case for doing well in the worst case, right? Which ideally is probably maybe what you want in some settings. From clued into clueless, right? When you had labeled samples to like you had no idea where your target is, but you thought they were similar problems and have some shared properties. They're like these set of methods that you should consider using. And, you know, if you have thoughts about things that, you know, don't fall under these settings, I'll be very curious to hear them. But I think for the most part, a lot of the problems we want to solve, we do have some like solution that should work if you are right about the setting you're in and want to consider them. And this sort of like gives hopefully a good picture of the solution landscape if you want to deal with distribution shift. And I'm going to skip very quickly to like the policy things. And so clearly the world is dynamic. And one of these dynamics is distribution shifts. Hopefully, I didn't need to convince you of that, but if you weren't convinced, hopefully you're convinced now from some examples. So the question is, as we continue to integrate ML systems to our day-to-day and critical infrastructure, how should distribution shifts factor into like AI policy? So like I train on ChatGPT, I've seen the internet. We can argue later whether or not that means you're IID with the world. I would say no. Let's assume I'm right. And so like from there, what might you do? And you know, the main thing I want to say is just like, and this is sort of like the primary question that I'm interested in these days. And so I think there are two questions. One is evaluation. And I actually think like, how do we evaluate models when we know that the world looks different than what their training set is or what our benchmark might be? And so the first question is external validity. So like, if distribution shift break performance, can they also break evaluation? And you know, what kind of evaluation can I expect to generalize, even though my benchmark isn't IID? And so one of the examples of this is this paper written by Ben Reck and co at Berkeley on sort of like, do ImageNet classifiers generalize to ImageNet? So basically what they did was they created an ImageNet test set V2, and they take basically all the models that people train on ImageNet V1, and then they validate on ImageNet V2, and then they said, okay, let me plot the original test accuracy versus the new test accuracy. And the thing they saw was just like everything dropped, right? Things dropped from like 10 to 15% accuracy, if I remember correctly. But what they observed is that the model ranking stayed approximately the same. So even though all the numbers dropped, when A was better than B in ImageNet test set 1, it was also better than B in ImageNet test set 2. But this is sort of like an internal validity statement, right? You know, maybe ImageNet test set 2 is a different distribution, but probably not. Same class. It was collected similarly. Lots of reasons this could happen. And so the question we actually care about is, do we have external validity of model rankings? And so the idea is just like, you know, from say 2012 to 2017, before my time, before most of our time, I think, people were trying really hard to improve on ImageNet accuracy, right? Like that, if you improve image accuracy by like 1%, that was a CVPR paper probably, right? And so people were going very, very hard at this. And this probably should have introduced some bias, right? In principle, there should have been at some point where like you only did better because you tested on it. You were sort of like using ImageNet as your test set, and presumably you would have done worse if it was some other data set. That's something, if you talk to a statistician, for example, they'd be like, yeah, this is a terrible decision to just like iterate on the same validation set that we've all been using as a test set. And so we wanted to test this. And so we created image not as a counter replication, anti-replication of ImageNet. And so like we basically took image not, has the same size, the same diversity, but very different class from ImageNet by construction. Also, we keep the 100,000 training examples per class, but now instead of coming from Flickr, which is sort of like a well-curated data, more well-curated than the web at least, and also we use LionB, which LionB is sort of like it's just a crawl of the web, right? It just goes on the web and collects image caption pairs. So it's much more noisy, less reliable, all of these things.
Don't say that here. We like Lion.
Oh, I like Lion too. Yeah, I like Lion too, actually. Never mind. And we also don't have any human annotator, so it's like a much more noisy data set than ImageNet is, like on purpose. So I use Clip to sort of like pair sort of the image and the caption, and then I use like BERT to pair labels and captions. So it's like very, very noisy data set. And so the idea is like, does this preserve ranking? So we have a counterfactual question there. Had ImageNet been image not, would something have changed? And it turns out that when it comes to model rankings, so this is just a classifier that shows whether or not you can tell the difference between the two data sets. What we see is that actually, if you look at image and image not only do the model rankings stay like very close, model rankings stay the same, for like the main models that people cared about, the relative improvement was also very similar. So what this says is just like, when VGG did better than AlexNet by like 1.25 or whatever, it will have done approximately that on image not as well, right? Which means that the improvement that it did on it, that improvement wasn't specific to ImageNet, right? It was more general. And so what we can take away from this is for like model development, right? Rankings sort of like should be preserved as long as you have a large diverse data set. Now the number, right? The number, that's a different story. But I would argue that the number is not something we've ever cared about. And here's why, right? Suppose I give you a data set and I give you the same data set, but I added 0.25 label flip noise, right? Like in principle, nothing about that data set changes, just the number changes. You just like change the label noise, but the rankings would stay exactly the same, but the number would change, right? But really, we use ImageNet to build better models. We didn't actually, most of us didn't actually say anything about the numbers. But today, for AI policy, we care about the number, right? I want to say, hey, this LLM that I'm going to put into schools to teach children, I have evaluated it, and this is a number that tells me that it's safe to use, right? And we've just never cared about the number, and we know that the number breaks very easily, right? If you don't have IID, I can't tell you anything about how well that number will generalize. And as we've established, the world is not IID often without training data set of our benchmarks. So this is like a huge problem. But at least we know that at least the best model likely on our training benchmark is going to be the best model in the real world. The number might just change drastically, right? And so the second question is, do we have worst case robustness? And I'll just spend 30 seconds on this and skip to the case that, there are a lot of papers that are showing this accuracy on the line phenomena, like very well cited paper that say that, for a lot of our benchmarks, the better you do in your P, the better you do in your Q, right? And the claim that what we just figured out is if I give you two models, one that is just the best in distribution classifier, so on your P, and one that's just the best overall, like best worst case optimal, only uses non-spurious features. The only way you can distinguish these two via like transfer accuracy is if you don't have accuracy on a line. So you either need like no strong linear correlation or you need a negative linear correlation. And what that tells us is that like most of our benchmarks seem to exhibit, for distribution shifts, seem to exhibit this property, and this property might actually suggest that they're not good benchmarks for robustness of distribution shifts, which means, when we want to make claims about how well our model might generalize to the real world, we have to be more careful about how we construct our benchmarks, and maybe we need to rethink how we're actually designing our benchmarks. And yeah, here's some funny acknowledgements, and yeah, sorry for going like 5 or so minutes over. Thank you for listening. I'm happy to take any questions or, over email or after, if you guys want.
You'll be here for the rest of the day.
I will.
Yeah, any quick question?
Thanks, everyone.